So finding screen pixel coordinates is what we're up to in this video. By the end of it, you will have the wonderful result that when we play the game, it will start logging out the number of pixels along the screen that white dot aiming dot is, and the number of pixels down the screen, or the viewport more specifically, that is. And we'll even tackle Windows scaling issues and all sorts. So let's go and get it done. So the next step in doing this job is going to be to what we call deproject the position of the little dot on the screen into world coordinates. We want to know what direction we're looking in when we look through that dot on the screen. So let's take a look at how we're going to do that. Start off in pseudocode. So in the get site ray hit location, this hit location equals f vector 1. That was purely for testing, and so that we are proving that we were changing the value. Remember, we set a value here, we pass a reference to it as an out parameter, it gets changed inside this method, and then we print it out. Okay, but now what we want to do is we want to know what actual direction we are looking in. So we want to get to the point where we can put the look direction logged out here as at least a next step. So what are the steps for doing that? Well, the first thing we need to do is find the crosshair position, or at least set the crosshair position. What else are we going to need? So we're going to need to deproject is the term they use. Screen the screen position of the cursor or crosshair to a world direction. That's what they call a deprojection. And then we're going to line trace through along that direction, which we would call a look direction, and see what we hit up to some maximum range. Wow. Okay, so definitely worth thinking about what the recipe is. Something like that. We're going to find out what the crosshair's position is, deproject that position into a world direction, and then line trace along that and see what we end up hitting. So it's going to take more than just this method. We're going to need a couple more helper methods below, but let's get started on it. And I think I'll challenge you to do part of this as part of this video, of course. So let's just get you off the ground. We're going to have an int32, a couple of int32, so you can actually declare them on the same line. We're going to call it size x and size y. In fact, we ought to be more explicit and call it viewport size x and viewport size y. Okay, so what are they? Well, they are just going to be the size of the current viewport, i.e., when we're playing the game, the viewport that the game is running in, the whole thing that's moving around as I move my mouse cursor. That is the viewport. Okay, so how do we get that? Well, we have a method called getViewportSize. And there it is. It's just immediately available to us, and it's going to use out parameters. Look, you can see that in the clue of the signature there, int32 ampersand size x, int32 ampersand size y. I would prefer to see the ampersand bound to the int32 to give us an idea that it's a reference to an int32, but it's basically how Unreal do it, so we'll just have no control over that. We'll just live with it. Get used to the ampersand being either side of the space. So we're going to pass in viewport size x and viewport size y, and these are out parameters, which is why I really want you to get used to them, because we have to use them, because a lot of the engine calls use out parameters. So next we want a way of the designer ideally specifying on the tank player controller blueprint where this reticule or crosshair is. Now, we don't, I think, need to go as far as actually reading the position of that dot from the user interface. I think that that gets changed so little that it doesn't matter if we have to change it in two places, i.e. if we have to actually go to the widget, move the dot around, and then come into the tank player controller blueprint and set some sort of parameter for the position, the relative position on the screen. I think that's okay. I'm generally against things being in two places, but two places is okay, three isn't. Two's okay, especially when the things don't change very often. It will reduce the complexity of reading from the UI. So I think this would be a great challenge actually for you at this stage, is for you to work out what the screen location is based on the viewport size and a couple of parameters that you will make. So let me formalize that in a challenge slide for you. So here goes your challenge. I hope it makes sense to you. I want you to create a couple of private member variables, crosshair x location and set that to 0.5. That is to represent the fact that in our game, the crosshair is halfway across the screen. It's the same convention as the UI anchors and the like. So it's 50% of the way across the screen. I want you to create another private member variable called crosshair Y location and set that to 0.3333. Now that's horrible, but it's also fine because we are accurate there to within 1 part in 100,000 or whatever, and that is far less than the number of pixels you're going to have horizontally, so we're plenty accurate enough. And this is exactly how things work when you set relative numbers in the user interface system. So it's consistent with that and it's fine. So have a crosshair Y location and it's the distance down the screen. So you can see that we're starting from the top left and that dot is 0.33333. Okay, it goes on forever, but that many decimal places is plenty of the way down the screen. All right, make them both edit anywhere for Blueprint so that the designer can, if he decides to move his little white dot, him or her can also change the position in code, or at least in a parameter. I want you to then calculate an F vector 2D called screen location. Now it's actually very simple, it just involves a couple of multiplications, but tying it all together is the bit that counts. So you're going to work out what the screen location is in pixels. It'll be a pair of floats specifying the pixel coordinates that we'll want to deproject later. And it will change as the viewport size changes. Not that that's likely to change while they're playing the game, but you get the idea, it's flexible. So go ahead, pause the video and see if you can make that work now. So welcome back, let's take a look at the code. Make these member variables first. So what did I say they were going to be called? I have to look at the challenge slide. Crosshair X location was the first one, so it's private. So, you know what I've done? I've made all these puppies here public when actually they all need to be private. So there's a mistake I can correct. All right, so here we want a U property. Edit anywhere. Spaces, no spaces, don't really mind, I'm going to leave it without. And then it's going to be a float because it's a fraction of a number, and it's going to be called crosshair X position. I think, I keep forgetting what I asked you to call it, location, whatever. Location. Okay, now make that 0.5. Fine. Indentation goes wrong because Visual Studio doesn't understand this macro. Okay, let's paste in for the Y location, because it's almost identical, and give it about 4 decimal places worth of 3s. All right, cool. I'm going to copy crosshair X location because we're about to use it. Save me retyping it and forgetting whether it's location or position once again. And let's think about what it's going to be. Well, we may as well use auto because it'll all come out in the wash. So screen location is what I asked you to create, and it's an F vector 2D. So hopefully you realize that you can do this calculation directly in the constructor of the F vector 2D. So what do we start with? Well, we're going to start with viewport size X, if I can type. And we're going to multiply that by this crosshair X location. So whatever the X viewport size is in pixels, let's call it 1,000 pixels wide. If the crosshair X location is 0.5, then we get a value here of 500 being returned for the X part of the F vector 2D. So at pixel 500 is where the screen location is in X, and then we do exactly the same thing in Y. In fact, it's so exactly that I would recommend copying and pasting and then changing X's for Y's to minimize the chance of boo-boos. Okay, that's fine. Now, if you wish, you can log this out as long as we are actually getting site rate hit location every frame. Are we calling it? Yes, get site rate hit location. Good. So I think it would be good practice here to do a UE log of what this is. So log temp, otherwise we don't know we've done it right. Warning, and then we're going to have a text macro because we love them. And I'm going to put some string in so that we don't get some horrible you shouldn't have 4 parameters warning, and also tells us what this is talking about. So screen location, may as well use exact variable name with a %s to say expect to find something that I can make into a string or display as a string coming afterwards, and then comma, and then we're just going to go screen location. And of course, the type of this screen location is an F vector 2D, must be because that's what we've constructed on the right-hand side. All right, let's have a look and see what we get. Oh, before I do it, let's just suppress this look direction log up here so that we only get one thing coming out. Now, with a log that's down deep in a function like this, rather than near the top of your class and at a high level, you want to get rid of that log pretty quickly because we don't want deeply nested methods, sub-methods logging, because it just gets really confusing trying to get rid of logs then. So let's just wait for this compile, see if it works. We should be getting, well, it depends on our viewport size. What is my viewport size here? Let's have a look. You could verify it using something like Snagit. You could take a screen capture, but it's probably 600 pixels, that sort of thing. We'll see if it's right. It'll be obvious if it's right. So note, see reference to function template instantiation, tank player controller 52. There's something wrong. So maybe the first thing to do is just have a look and see if you can see what's wrong with it. What is wrong with it is screen location, of course, is an f-vector 2D, and what we need to do is something like a toString on that. So we do a toString method, and then we need to do a star in order to turn this string back into a tchar star, that old chestnut. Let's try again. Quite cryptic errors, I would say. That's not an error that, unless you've got some experience, which is why I'm showing you these types of errors, is too easy to deal with. But don't get too caught up in those massive, long, complicated errors. Just go back to your code, take a look at it, and say, well, the first look at it, what's wrong with it? Is there something obviously wrong with it? And to me, there was something obviously wrong with it. You don't need to go through and read every nuance of that error message until your first couple of gut feels don't work, I would suggest. Otherwise, the sheer time it takes to read the full width of the error message makes it not worth it. But of course, don't leave it too long before you do read that error message carefully if you're still stuck. So let's play. Here we go. Look, 402 by 179.4, blah, blah, blah. That sounds very feasible. I'm going to just load up Snagit so that you know what I was talking about when I mentioned Snagit earlier. I think I've got a keyboard shortcut set up for it. I have. I'm going to screen capture the middle portion of my screen there, which is the viewport. This will also highlight to you what the viewport actually is. I'm going to look at the size of that, if I can find where it's stored it. Bless it. And then we can see here that this is roughly 1000 by 677 pixels, this bit. I've got the pixels a little bit wrong. I didn't cut it that carefully. So let's just see if we're getting roughly 500 and something by 350 something. So we're not getting that. We're getting 400 by 179. So the likely reason is because if I look at my display settings, I've got 125% scaling on my Windows display scaling, just to confuse things. So if we take this 402 in a calculator and go 402 times 1.25, we get 502 pixels, almost exactly what we'd expect. Let's try the same in the Y. 180 is good enough for 179 times 1.25 gives us 225 in the Y, as if the total height of this thing was, I've got to think about this a bit more carefully. 225 is the number of pixels once we've changed, because of my strange screen scaling, from the top of the screen to the dot, which is a third of the way down. So we need to multiply the 225 by 3, which gives you the 675. Wow, at last. And then if we go back here and look, well, it was 677. Sue me, it's only 2 pixels out. So after a lot of combobulating, I think is the word I'll use, we have actually got the right place. As I say, let me reiterate, the reason it didn't come out exactly is because I have display scaling going on my screen to keep things visible for you guys. So pixels ain't pixels, they don't map one to one. That was all good fun. So hopefully that makes sense. I'm just going to go in and remove this log message, as I said we should do. And we actually have done the first bit, which is find the crosshair position in pixel coordinates. And that's what all this stuff here does. And that's what we've done by doing our intermediate variable and composed an f-vector, etc. So relatively simple revision-y stuff for you, and I'll see you in the next lecture.